So as you can see from the first order condition for the Nash bargaining solution, the framework assumes that each party has the same bargaining power, right? Because if each party has the same utility function, the utility functions are the same for both parties, then each person gets half of the surplus. Now, the generalized Nash product is an attempt to introduce bargaining power into the Nash bargaining solution. And here I'm leveraging from the wonderful textbook by Bowles called Microeconomics, Behavior, Institutions, and Evolution on page 177. And the approach is as follows. You've got alpha, which is still the share of the surplus going to the first person, who is getting V of X, utility V, defined over X. And small z is the fallback position for the first person. For the second person, they get a utility function capital V, defined over whatever remains to them, and their bargaining fallback position is capital Z. The generalized, I'm sorry, this here is X, not alpha. The generalized Nash product is the product of the utility gain over and above the fallback position. So for the first person, it's V of X minus Z. But we assign alpha, which is a measure of the bargaining power of the first person. And this is multiplied by the utility gain of the second person over and above their own bargaining solution, which gets an exponent 1 minus alpha, which is the measure of the second person's bargaining power. Alpha is, by the way, a number between 0 and 1, and so is X in this framework. So here I'm trying to maximize the product of utilities, which is the same thing as maximizing the sum of the logarithms. So I'm trying to maximize the following expression. Okay. And this is convenient because it allows me to drop the exponents, which is going to make the derivation of the first order condition easier. So my first order condition, you have to remember how you take the derivative of logarithms. For any logarithm, you simply take the ratio of the derivative of what's inside the logarithm divided by the function inside the logarithm. So I'm getting alpha times v prime of x, z drops out, divided by v of x minus z, plus 1 minus alpha, v prime 1 minus x times minus 1. Why? Because the chain rule I also have here, I have to take what's inside v, because v is not defined over x, it's defined over f of x being 1 minus x. So I take the derivative of that, z falls out, and this is divided by this. Okay, this must be equal to 0. Now I can rewrite this expression as follows. I've simply moved things around. So it's very easy to see here that if alpha is equal to 0.5, then alpha equals 1 minus alpha. And this drops out. And so I'm simply left with the ratios of the marginal utility gain divided by the total utility gain, right? And this is true for both parties. So I'm back to the normal Nash bargaining framework. But this generalized Nash product allows you to express this with more generality, where you can set the bargaining power to something other than 0.5. And so you can introduce differences in bargaining power. And I'll just add that, of course, the Nash bargaining framework also assumes that you can normalize both utility functions as being independent of origin. So you can pick 0 as the origin, and z just falls out as well. So this is the first order condition that we've just derived for the generalized bargaining solution. And I'm going to develop this expression a bit further to try to show you some interesting results. So if you just bear with me. So I can rewrite as follows. Just sort of cross-multiplying. Okay. Now here I'm going to simplify this, I'm going to simply assume that v of x is x, and capital V of x is x. And of course capital V of 1 minus x is 1 minus x. And the reason I'm doing this is just to simplify this a little bit. So, continuing, I get alpha times 1, because v prime now is simply becoming 1, now that v of x is x, times 1 minus x minus capital Z is equal to 1 minus alpha, times v prime becomes negative 1, because I'm looking at the derivative, but the function is defined not with respect to x, but with respect to f of x being 1 minus x, so derivative using the chain rule is negative 1 times x minus z. Okay. So here's where I'm at. This is multiplied, all these things. So here's the first order condition that we have just derived for the generalized bargaining framework, Nash bargaining framework. I want to manipulate this expression a little bit to get to some interesting results, so bear with me. So I'm just rewriting this as follows, cross-multiplying. Now to simplify this, I'm going to give actual functions here for the utility functions. I'm going to say that v of x is equal to x and capital V 1 minus x is equal to 1 minus x. So let me rewrite this expression. Alpha times 1 times So here is the first order condition that we've already derived for the generalized Nash bargaining framework. I'm going to manipulate this expression a little bit to get to some interesting results. If you just bear with me, I'm going to do cross multiplications. Okay. Now to simplify this, I'm going to give actual utility functions for v of x for both parties. So I'm going to define that v of x is equal to x, and v of 1 minus x is equal to 1 minus x. So let me rewrite this. This expression simply becomes alpha. B prime is simply 1 times 1 minus x minus capital Z is equal to 1 minus alpha times. So here it would be tempting to write negative 1 here, but we've actually already done that. We've already done the chain rule for the derivatives. So this is actually just multiplied by 1 because we're looking at here the derivative with respect to everything that's inside the function and not the derivative with respect to x, times x minus z. So here I get negative alpha times x plus alpha times 1 minus z is equal to 1 minus alpha times x minus 1 minus alpha times z, which is equal to, let me further develop here, x minus alpha x minus 1 minus alpha z. This is removed on both sides, and I can rewrite x is equal to alpha 1 minus z plus 1 minus alpha small z. Now what does this expression say? It says that the share that goes to the first person, the share x that goes to the first person, is simply their fallback position z. I'm sorry, let me just develop this expression entirely. So you get alpha capital Z, negative alpha capital Z, plus alpha plus small z, negative alpha small z. And you can factorize everything by alpha. Sorry, let me do this again since I was running out of space. So let me just redevelop this. Alpha minus alpha z plus z minus alpha z. Right, now we can write this is equal to z, small z, plus, let me factorize by alpha. Alpha times 1, right, here it is, minus capital Z, here it is, minus small z, here it is. Now, if you look at this expression again, now it makes sense. The share of the surplus which is going to person 1, x, is none other than their fallback position small z plus a share of the total surplus. The share of the total surplus, total surplus is 1 minus the fallback position of each party. This is the total wealth which is being created, right? And person 1 gets a share of that, which is determined in terms of their bargaining power. So this is alpha, right? And so I can see that when alpha is equal to 1, so that person 1 has all the bargaining power, then person 1 gets 1 minus z as their share of surplus. So they get every possible gain that the other person, that is generated for the other person. So that's just another way to think about this result.